Hello there, geometry peeps. Today we're going to talk about methods of triangle congruence, and what we're going to do is we're going to review 6 different methods, 5 of which can prove congruency and 1 of which does not. Alright, so we're going to examine each of those and take a look at the properties of each of those. So the first one we're going to talk about is what we call side, side, side. And basically what it says, if you have 3 sides in a triangle the same size as 3 sides in another triangle, then the triangles are congruent. So if this is the same as this, this is the same as this, and this is the same as this. Now, one way we can think about this is to think of if you had 6 toothpicks. Alright, there's only one way you can combine them if they're all the same size to make a perfect triangle. So if all 3 sides are the same, there's only one possible way for them 3 to connect at the ends and make a triangle. And that possible way has to be the same in both instances. So that's why side, side, side can preserve congruency. Now, there is another property that goes along with this. Let's say I had a picture like this, and I said this is the same length as this, and this is the same length as this, and I had a third line in there that made that. Now notice we have 2 triangles. Now we could say this side and this side, so one side matches up, 2 sides match up, but where's the third side? Well, the third side would be itself, because if you drew 2 triangles, okay, this side is actually the exact same side in both triangles because it's shared. So this is what we call the reflexive property. Reflexive property. So when proving side, 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 or the other methods we'll get in here in a while, you can use the reflexive property if a side is shared in both triangles. We know that it's congruent to itself. It's the same length as itself. That makes sense. Alright, so that's side, side, side. That's our first method. The next one is side, angle, side. Okay? Side, angle, side is SAS. And what it says is this. If I have this side, the included angle, and another side, so if those 2 are exactly the same, there's only one possible length, one possible side that can connect these 2 exactly. And if that's the case, the triangles are going to turn out to be this exactly congruent. And think about this. This is the same length as this, and this is the same length as this. And if you put the 2 pieces together, this opening has to match exactly this opening. So there's only one piece that can fall directly into place. So that's why side, angle, side preserves congruency. Now, where you're going to hear this word a lot, and I'm going to say included angle. The included angle would be that one that's sandwiched between the 2 congruent sides. So notice if we had our tick marks here, I would have side, angle, side. Congruent to side, angle, side. Over here we had side, side, side. So again, side, angle, side is a relationship, and that's the reason why. Okay. Now number 3 here is what we call angle, side, angle. ASA. Now, so this is when the side is included. So it's this angle, this side, this angle, to this angle, this side, this angle. And if you think about it, angle, side, angle. Angle, side, angle. Alright, now, the reason this one works is because if this opening is stuck like that, because they have to be the same, this opening is stuck like that, and the distance between the 2 openings, what's going to happen is this point is always going to meet at the same thing. So even if I drew these lines as long as I wanted to, if these openings matched exactly and they were the same distance apart, they're always going to cross at this same point. Okay, again, that's why they preserve congruency and that we can say they're congruent. Alright, so angle, side, angle is another method for that reason, that this point's always going to fall, so by default, our other pieces are also congruent. Alright, and that's what it's all about, is that there's no possible way I could create another triangle with this angle, and that side stuck in between that would be a different size. Alright, it's impossible. Alright, now our 4th one is angle, angle, side. Alright, so this is in a different order now. So it's angle, we kind of skip a section, angle, side. Angle, angle, side. Alright, and again it goes back to if this opening is stuck like that, this opening is stuck like that, and this comes here. This is the only side that we can mess with, and no matter where we draw it, it's going to connect right at that same distance, right at that point. So therefore, angle side, angle side. Now notice as I'm going through all this, notice they were consecutive, angle side angle. Here it's angle, we kind of skipped one side, angle side. You can never skip two things. So if you think of a triangle as having 6 pieces, okay, if you go angle side angle, angle side is okay. Notice how I skipped this one. That's fine. You can't skip 2, so I couldn't go like angle, skip, side, angle. That's not allowed. Okay, so they got to be consecutive, but it's okay to skip 1. Alright, so that's how we kind of help identify it. That's why. Now for 5, okay, this one's going to be angle, side. Now this one does not preserve congruency, and don't try to write it because it would be inappropriate. Now, if we have a triangle, let's say. Alright, so this is angle, side. We would skip that angle, and then this would be the side I'm going to refer to. So this is the side I'm talking about as I change it over here. So this again, we're going to try to recreate that triangle. So we have angle side. Now, I actually want to do a dotted line here. So now, what it's saying is that this angle and this side are locked in place, because that's what this says. It has to be the same. But what happens is this angle can actually flex back and forth. So this side could swing either out or in, and there's nothing constricting it, because those don't have to be the same. Those angles could potentially be different using this method. So angle side doesn't work, because what if I did this? Okay, so I still have my side and my angle, but this time it's possible for me to swing it inward and still be congruent. Okay, whether I swing it outward, I can bring it inward. And notice if I brought it inward, it wouldn't go exactly up and down because that'd be 90. But if I swung it in a little further, the side could actually keep its same length. But yet, look, you can tell these are two different triangles. Right? This is more of an obtuse triangle. This is more of an acute triangle. So angle side does not prove congruency, because this angle at top here isn't locked, and I can swing that side back and forth to create different size triangles. Pretty much too. So it doesn't guarantee that this side's going to fall directly in place. It could fall here, or it could fall inside like that, still being the same length. Alright, so that's why angle side doesn't work. But there is one special case, and we call it hypotenuse leg theorem. Okay, or sometimes we say HL. And what that says is there's one specific case where an angle side relationship will work, and that's if we have a right angle. Now, if we have a right angle, we know the hypotenuse is this piece here, and then either leg, let's just say this leg. All right, now if you notice, it's in angle side relationship, but we know angle side doesn't prove congruency, except for if it's a right angle. Alright, so the reason for that is this. If I have a right angle, and I know it's this side and this side, what happens is, because this is a right angle, this piece is the same in both triangles, so it's going to fall in, and it's got to hit this line right at that point. No matter how big I draw this line, okay, well, I shouldn't do it up top because we know this one's stuck. So this one's a certain length. This line could extend forever, but if this piece is the same in both triangles, wherever I drop it in, it's going to hit at both these points. Alright, so what we learned today is that we have 5 ways to prove triangles congruent. We have side, angle side, angle side, angle side, and HL theorem. Okay. Sometimes you might see HL written with a little r here for RHL, and all that r stands for is that right angle hypotenuse leg. You can put it or you don't have to. It's up to you. All right, but that's all I got. See you when I see you.